Okay, let's get started. So the last time, we learned about cotangent bundle and so on, and differential form. And at the end of the lecture, I start talking about the integral differential form. So we just recap what we have learned about the integral differential form. So now M is now always n-dimensional, orientable. Mathematical, and being omega is it's called top form. And then we want to introduce the notion of integral omega. So integral omega, that's what we want to introduce the notion. To do that, so again, we use the local chart or atlas to so atlas for the manifold, and here in open subset in R you can do the integration by using so this locally omega here, locally omega can be written some let's see. dxn. So that's what. We need. So locally we can just integrate this form. And now, so we want to patch everything together. So each open patch, we can use local coordinate to integrate for integration. But the question is how we do the integration for whole manifold. To do that, again, so the intersection is very important. So the intersection is important, and we introduce so-called partition of unity. So that so there's a smooth function, collection 3 smooth function for each so here you have a U, and the other part is V. So at the intersection, you have if you add two functions together, you get 1. You get 1. So that's a partition of unity, and also we need to find the so-called locally finite. So locally finite open cover. So locally finite means that the so in principle, given a point P, there is infinite many. There can be infinite many open patch around the point P, but we want to avoid that to define the integral. So we want to have only finitely many open cover. Open, how to say it? Finite many cover around the point P. Okay. So that's called locally finite. Finite open cover. So the point P, there is no like infinite many open chart that actually cover point P. If there is an infinite many open cover, we cannot define the partition of unity. Okay, so we want to finite many cover to define partition of unity. That's the notion of the locally finite. So given the partition of unity, given an atlas, so given an atlas U, alpha and phi alpha, then one can, and this is locally finite, so locally finite open cover, one can construct the partition of unity whose summation is equal to 1. Then now, so the omega, integral of omega over m can be understood as sum over alpha chi alpha omega of essentially the u alpha. So that's one can do for the locally finite open covering. That's how you can define the integral over the manifold. So at each open chart, one can do the integral, and we just set up some partition unity such that the at the overlap region you don't have double counting. So you don't have double counting. So at the overlap region, you have properly count. So there is an important theorem. Let us consider the manifold is oriented manifold with boundary. So then, so this is n-dimensional. So boundary manifold is for instance, so in particular we are thinking about something the situation M and the boundary of M. So this is n-1 dimension. And then so what we have is that the so here we assume that omega has no like a is M has compact support. For instance, in particular, so for instance, one can take the following region in R2, right? For instance, R2, we can have the following region. But if you try to do the apply the Stokes theorem on this region, you have to be careful what's going to happen in infinity, right? You have to infinity in addition to this boundary. So this is M and the boundary M. But if it is not compact, you can have like go to infinity. So that we want to avoid the situation. Okay? So this situation is not good to apply for Stokes theorem. That's what I mean compact support. Okay? So this Riemann surface with boundary has a compact support. So this is not good situation. This is not good situation. So therefore, we want to have M. You want to M to have the compact support. Okay. In particular, if M is the closed manifold, so So which means without boundary, without boundary, d omega m is always 0. So since without boundary, so you don't have right hand side. So if you have so-called d omega, integral d omega over the manifold, so of course d omega is now in omega n. Because here omega has n minus 1 and d just increase the degree. Okay, so that's Stokes theorem. You will learn. This is generalization of Stokes theorem you learn in the electromagnetics. I posted homework 3 just this morning, and it contains the homework that will try to relate so Maxwell action to the differential form. So, any questions so far?
I have a question.
Yeah.
I still don't quite understand what the specific meaning of this second condition in definition 4.10.
Oh. So the so support of chi alpha means that the chi alpha is non-zero. So let's see, x in the manifold, the point P of manifold here, chi alpha of P is non-zero. That's what we mean. So which means that the only the open chart it can have non-trivial configuration, non-zero configuration. But apart from this open chart, it becomes 0. That's what it means. Any other questions? Okay. So Dramko. So we introduce differential form, and we start talking about the Dramko homology. So this is going to be a bit more interesting. So now we talk about the vector field and differential form, and we try to understand how this differential form or vector field encode the information on manifold. So now we introduce the external derivative or differential that map omega k plus 1 of m, and so that the and also we know that the dd is equal to 0. Okay, actually it's a good exercise to do to check d square is equal to 0. So this is very fundamental. Even though I didn't include it in homework, it's better to. And then we call it zk of m. Is this is in the closed form. And the bk inside omega k is exact form. The kernel of D, which means that the omega k is such that the omega equal to 0. And this is image of D, which means that the either, sorry. So So cross form is just that if you apply D, you get 0. That's a cross form. Exact form is you just have the expression as a D of something, some other lower degree K-1 form. That's exact form. So D squared is equal to 0 means what? There is some relation between them. Close an exact form. D squared equal to 0 means what? Speak out. If you apply one more time D in here, you get 0 always. So therefore, ZK contains, so closed form contains the exact form. The set of ZK contains BK. And Drum did something very, very simple thing, but a very clever thing. So again, here it's a vector space. It's a vector space. So we can have the quotient space. So this is the construction of Drum cohomology. So you just divide ZK by BK as a quotient space. This is Drum cohomology. So Drum cohomology is at the so you can each time you can apply differential exert derivative. So once you apply D, sum the form. So this is ZK, Z0. So sum of the form all map to 0. This is the kernel of D. Sum of the form just map to some non-trivial element in omega 1. Okay? And now we apply the same thing to here. The same differential form or the exert derivative on omega 1. And since, so this is the image of D, so what is it called? This part is called exact form. So this is B1. This is B1. Okay. And this B1 is sent to where? Under the exert derivative? 0. But not all element that goes to 0 is contained in B1. Some other form I'm up to 0. So the difference between, so this is difference, or maybe it's better to write bigger, a bit bigger. I think it's better to write a bigger in this case. So omega 0 is here, and the map to here. Maybe it's better to exaggerate a bit more. So this part is B1, whereas this part is Z1. And the difference between them is first drum cohomology. Okay? Not all elements are in the B1. The exact not all elements in closed form are in the B1. Some elements are not inside the B1. And the difference between Z1 and B1 is called, as a vector space, is called the drum cohomology, first drum cohomology. You can do the same exercise to the other part of the differential form. So here, omega 2, some elements are mapped to 0. Under the differential or external derivative, on the other hand, you have there is some difference between closed and exact form. That is second drum cohomology. Second drum cohomology, and then you can go to up to n. N is called drum cohomology. For instance, if you have X and then H drum, so this is vector space, so you can have addition, notion of the addition. And then if you have two elements in drum cohomology, one can take just wedge product of which product, and you can just apply D such that the so this is what? Just speak out. Just speak out. This becomes what? Once you apply D on which product, what you get is what? But here you assume X and Y are drum cohomology, elementary drum cohomology. 0. So therefore, X which Y is also K plus L's element from drum cohomology of N. So you can have, so once you have consider collection of the drum cohomology, the star can be run from 0 to N, and consider which product, this form called so-called ring. Ring means you have addition and multiplication. So addition comes from vector space. So maybe I should write down more precisely. I transpose 0 to N. And this one is which product will give you multiplication. So that if you can define the addition and then the multiplication, this in mathematics is called, it forms a ring, or sometimes called R algebra or whatever. Ring or algebra. So this is called drum cohomology ring. And in homework, yeah. Do you know the example of ring? What is the example of ring? Polynomial. It's called polynomial ring. Another example? So polynomial ring is sometimes called like this way. This is a polynomial ring. this is the element of a function such that it has a form and the AI are maybe real number. So it has the addition and multiplication. That's a polynomial ring. And in fact, these, for instance, the just integer is also form have a addition and a multiplication. That's the ring also. Anyway, and the important is a Poincare number. Drum cohomology of Rn is so what is the base that stands for this R? So if you consider drum cohomology of the just plus space, the non-trivial element only localized in 0th degree. Is that what it means? The Poincare lemma. What is the element that gives the base of this R, this vector space? What is the element? Here, 0 is mapped to omega 0. So B0 is what? B0 is what? Zero is mapped to omega 0. What is the image? What is the B0? Just look at the definition and it's applied B0. What is B0? It's a very simple question. So B0 of R n is just some form that's omega 0. Omega 0 is just function, okay? Which is the differential of some function minus 1. What's minus 1? Omega minus 1 is just 0. So what is B0? 0. So what is Z1? Z0? Huh? R. Some people say R. And what is the R stand for? Constant function, good. So on R, Z0 of Rn, which is some function, omega 0, this is just function. When you apply d omega, you get 0. Okay? So which means it's just constant function on Rn. Okay? So we want to find a just number, alpha, such that any point x is mapped to alpha. Okay? That's constant function. Once you apply differential or extra derivative, you get 0. Okay? So therefore, this R is indeed stands for this constant function alpha. And alpha varies this R direction on the image. That's Poincare lemma means. And furthermore, if you find so locally, so it's on R, so all the differential form can be written. So if you look at the higher degree, all the case element and of the so all the form, higher form that is in closed form is just a sum of some differential times constant. Okay, once you apply D only look at this constant one and you get 0. Okay, and this Poincare lemma said there is some image for this one. Do you understand what I mean? So this is omega. So d omega equal to 0. Okay, but this one is actually contained in BK. Therefore, it's 0. Drum cohomology 0. Drum cohomology 0 means there is no gap between BK and CK. In the case of Rn, in the case when once you pick manifold as Rn, there is no difference higher cohomology. Okay, so there is no difference. So therefore, given the closed form, there must be an element in the lower degree such that its image under this D is equal to omega. Okay, what is the element? Can you find? What is the element? So what I meant is there's a exist either in omega k minus 1 Rn such that d either is equal to omega. That's what it means. That's Poincare lemma set. What does it mean? And so can you find the either? Can you find an error? It's very simple. Error can be something like this one. See? So just get rid of D here. The first one, get rid of D here. Once you apply D either, D only see this one. If you apply D other part, you get 0. So this is the either you can construct. For instance, you can have another either up to sign. For instance, instead of get rid of D in front of I1, you can get rid of somewhere else. But you need to be careful about sign in that case. That's it. So there must be multiple elements that goes to the same element omega. You understand? Any questions? That's a Poincare lemma. And in the homework, I ask, so if you change, so this is flat space, Rn is a very flat space. But the reason why this simple construction is give you very, very powerful tool is that it contains the information about the manifold, topology of manifold. So if you consider drum cohomology non-trivial manifold like a sphere, RPN, and whatever, torus, and so on, you get the different answer from this flat space. Okay? It contains the information on topology of the manifold. So in the homework, you are asked to compute the drum cohomology of the sphere and torus, and look at the explicit form of the drum cohomology and the element of drum cohomology. That's what you're asked to solve. And in fact, this drum cohomology is topologically invariant. And one can compute so dimension of HK drum of M is called case Betti number. So and from here, indeed, one can compute if M is the, for instance, if M, from here one can compute Euler characteristic. Euler characteristic for higher dimension manifold. That's, we are going to that reaction we are going to, okay? To which we are going to. Any questions so far? Okay, to see to compute the, for instance, Euler characteristics and so on. So we need to do a bit more preparation and so on. And then first we introduce. So now we just consider vector field differential form, and after that we introduce drum cohomology. And to consider drum cohomology and so on, we just want to add a bit more structure on the manifold. So that's what we are going to do. The structure we are going to add is called Riemann metric. So Riemann metric is essentially a manifold with so-called symmetric true form. I'm going to introduce. So this is called Riemannian manifold. So the notion is first given in Riemann in around 54 or something, as far as I remember. His famous speech on the Göttingen. Riemann made a huge, contribution to the geometry, or he essentially created the area of Riemannian geometry and the algebraic geometry. He made a really significant contribution to the mathematics. But his idea is, at that time, no one cannot formulate, couldn't formulate his idea. But as time goes, the many mathematicians formulate his idea, and nowadays called Riemannian geometry, algebraic geometry, and so on. So that's what we are going to learn. But essentially, what Riemann considers is just given a manifold, higher dimension manifold, and adding Riemann metric, one can measure the distance between 2 points. Measure the distance between 2 points in a manifold. So given a manifold, and now we only have vector field differential form and so on. But given a point P and Q, what is the notion? What is the notion of the distance? So we don't have, so far we cannot measure the distance between P and Q. Okay? We can have a path, whatever path we can have. You can have lots of paths between two, but how to measure the distance between them? So the Riemannian metric actually by using the Riemannian metric, one can introduce the concept of length. So G I mean, physicists, I mean, just if you ask physicists, whatever, long time ago, what are the metric? People just write down G mu dx. What is the metric? Riemann metric. People just write down, this is Riemann metric. That's what the physicists usually, I mean, long time ago mentioned, but that's not right way to introduce the Riemann metric. So the Riemann metric is the bilinear form for tangent vector to R. So this is bilinear for any P, such that it has the following property: xp, yp is equal to, it's symmetric, and then positive definite. And non-degenerate. So this is called symmetric. Once you swap x and y, some tangent vector at point P, you have the same body, and here you just have positive definite. If you measure take the inner product of the tangent vector with respect to this metric, you get always positive. This only becomes zero when the tangent vector itself is zero. So that's non-degenerate. For instance, if you take the local coordinate at the point P, one can have the local coordinate phi is equal to x1 dot xn. So this is local coordinate. Then the tangent vector has the basis, and one can apply the metric on this basis. This is what usually people write Gij at point P. So therefore, usually the physicists write Gij dxi cross dxj. Okay. Cross dxj as a metric, but this is only expression by using local coordinate. So this is coordinate-free way to mention. So first, in terms of this local coordinate, the first condition is just replaced by, so Gij is just matrix, and by n matrix. The first condition is Gij is equal to Gji. Okay. The second condition is Gii is always positive definite. Okay. And the second condition, determinant of Gij is non-zero. So that's this is positive definite. This is the non-degenerate. So that's the coordinate. The physicist likes to explain how the Riemann metric, but without color, you can just introduce the notion of the symmetric, positive, and non-degenerate in terms with coordinate free way. So that's mathematician likes it. And then, furthermore, so this Riemann metric. So now we assign only the bilinear form at the point P, but here. G can be varied. P is in smooth way. So G can be smooth in the sense that once you vary P, oh, I see. I think there's a typo in the election note. So what I meant, smooth means that the assignment P goes to GXP, YP, and once you move P, this assignment is smooth. That's what it means. Okay. So any questions so far? There is some complaint about the how the black ball look like from camera, so I just let me cross. Okay, so now given the Riemann metric, one can just introduce the notion of the length of the vector, tangent vector, which is just the square root of this one. And then, so given the curve gamma, so here at the point P, at the point some point X, so one can just always have a tangent vector for gamma. So length of gamma indeed dt 0 to 1 gamma dot t. Or maybe A to B, such that physics is usually right like this way. So essentially what it means that so now gamma is some map from A to B inside R to the manifold M. So literally you have manifold M and you just map point gamma, and at each point T one can assign vectors, so which is gamma dot, this is tangent vector, this is dot. Don't forget about dot here. So it's just derivative with respect to T. At the point, one can just have the tangent vector for this curve. Okay? And now, so Riemann metric will give you the notion of the length of the tangent vector. Okay? And you just integrate the length of tangent vector along this curve. Okay? That's what you mean. That will give you the length of this curve. So therefore, very, very roughly speaking, so Riemann geometry is just studies the manifold that a geometry of a manifold in which you can introduce the notion of the length of the curve, roughly speaking. But this very, very simple concept of length will give you a very, very rich subject. Riemann geometry is a huge subject in mathematics, and it has very, very long history. So let me move on. So now, we introduce a notion of the Riemann metric, and here you have, again, you can consider a map from M to N, and smooth map M to N. How we like to understand how the Riemann metric behave under this smooth map. Essentially, so this, it at the beginning, so I just write that. I think I need to check video. So x mu, wedge x mu. This wedge is not true. Actually, it's a symmetric product. So it's not the differential form. So it's a, if you swap mu and nu, you don't get sign. Okay, it's a symmetric. So you shouldn't write a wedge. Okay, if you swap, if it is a wedge product, if you swap it, you should get minus sign. Okay, this is not the case. So that's why I just use this tensor product. So that's not the wedge product. So this is the differential form and second symmetric differential form, which is symmetric under the swapping of dxi and dxj. So therefore, what should I mean, and take symmetric part. This S means the symmetric part. If you take tensor product of one form and then look at the only symmetric part, that's what it means. So symmetric part, so that's inside a metric with ellipse. Okay. So we know that this differential one form can be pulled back, okay, under the smooth map. Whereas vector field can be pushed forward under the smooth map. So we did the same operation. So given the manifold G and G, so this is Riemann manifold, one can have induced metric on M by pulling back the metric from N to M. Okay. In such a way that the F star of G xp yp is equal to G F star xp and then F star yp. So here, inner product is taken in the manifold on N, okay? N. XP and YP are vector, tangent vector. So this is XP and YP is mapped to, by push forward somewhere else here, around here. So this is the F star XP and then F star of YP. F star YP. So you can just push forward the tangent vector. From here, you have a metric G. So you can have one can have a product between two tangent vectors. This value should be the same as the induced metric, the product of x and p under the induced metric. Okay. So therefore, by using this construction, one can pull back the metric from N to M under smooth map, and this F star of G is called induced metric. Any question? Particular cases, so given a two Riemann manifold, and there is a so-called diffeomorphism. such that the induced metric G is equal to induced metric under this smooth map. If G is equal to F star of H, I think I should use upper one, sorry. F star of H, this is the pullback of the metric H to N, okay, under this smooth map, diffeomorphism. If this is the case, F is called isometry. And your homework, you're asked to do the following. So there is a standard metric on Rn. What is the standard metric of Rn? Huh? Yeah, so standard metric Rx is just identity matrix with respect to standard local standard coordinate. So this is standard metric of Rn, and then we know that the Sn minus 1 is mapped to Rn by just embedding you just look at the unit circle, unit sphere on Rn. So this is inclusion. So here you have a metric, so let's call this is G. So now here you have a G. One can have the pullback of standard metric Rn to Sn minus 1, okay, by inclusion. So here you can have induced metric I star of G on the unit sphere, okay, Sn minus 1. So you can just pull back. So this is the usual notion of the sphere. And we want to consider the so when you want to consider the distance, the curve, or the length of the so the length of the 2 point or distance of 2 point or so length of this curve, so you can just measure the distance, the length of the curve by using the standard metric, the induced metric coming from Rn. So that's the standard intuition we have indeed. And then, for instance, in SON acts on Sn minus 1 as a diffeomorphism. So for here, it's the figure of S2, and so in the homework you already did the homework. SO3 acts on this S2 by diffeomorphism. The rotation with respect to x, y, z axis will give you diffeomorphism on S2. And this diffeomorphism does not change the metric. Okay, so it's just the rotation does not change the unit sphere. Okay? So therefore, the rotation SON diffeomorphism acting on Sn is indeed isometry. Does not change. Okay? However, one can construct, so this I just consider this is R3. Okay. R3 to, okay, so it's a good, good exercise to do. Whatever. R3 to the sum. Okay, I think it's better to be smooth. So maybe some smooth bottom. In R3, there is a diffeomorphism to some smooth bottom. Sorry. From S2 to some smooth bottom, like this way. One can consider this is a diffeomorphism. It doesn't change the topology, and it's still smooth. Okay. So now I just consider some smooth bottom inside R3. But this, if you consider induced metric from R3, they are not. This map is not isometry. Okay. Definitely. The map between these 2 points are different from the lengths between these 2 points. If you measure the length by using induced metric. And of course, this isometry forms the groups. So this is one particular example for isometry. So the group that is formed by the isometry is called isometry. So any questions so far? For instance, another example for so other example for the isometry is that the Rn, what kind of isometry and stoichiometric I consider over there. What kind of isometry you can consider? Huh? Could you repeat again?
Translation.
Yeah, translation. So here, the isometry is formed by group, but one is the map, the Rn. The point is just a translation by vector v. It's a translation. Another is rotation. On acts on Rn. Okay, so this is rotation.
Reflection.
Huh?
Reflection. Also.
Yeah, rotation plus deflection or orientation reversing. Okay, deflection. So this is SON, and then here you have the determinant flip. Determinant of matrix is minus determinant of so determinant flip. On determinant of element G, I shouldn't use G. A can be plus minus 1 for when A is element of On. So it's a two-disjoint union of the SON. So they form so-called, sometimes it's called, so this is called the translation plus, so this group is called Euclidean group. So these are isometry. So these are isometry of Rn, and they form the group, and it's called the Euclidean group. And just in physics, people just usually use in the R 1 comma n minus 1 such that it depends on notation. People just use this Minkowski signature Okay, in Gauss differential, there is a minus sign and the other is plus. Sometimes it can be opposite. Depends on rotation. And if you consider the isometry of this R1, n minus 1, isometry group is called the Poincare group of the Poincare group. Essentially, the analog of rotation and the deflection. So, which is called this is indeed translation, or sometimes it can be Lorentz boost plus O1, n minus 1. Okay. So it's the rotation, the Minkowski analog of rotation and deflection, or which is called Lorentz transformation. So this is called Lorentz transformation. Any questions? And if you consider the manifold, Riemann manifold, Mg, and if you consider vector field, okay, and the vector field generates the flow. So vector field, yeah, I think I should write them like this way. Is flow one parameter family of one parameter group of the diffeomorphism phi t. In particular, so if M is if M is compact, a compact or for instance compact and orientable. It's if it is nice enough Riemann manifold, compact or closed, one can have a flow for any t, and then if the phi star, the phi t is diffeomorphism. So diffeomorphism, M goes to M. Okay, and one can pull back the metric G, so it's now Riemannian metric. Riemannian manifold. So the metric can be pulled back by this diffeomorphism. And if they are the same, pullback metric is the same as the original metric on M. This is called X is called Killing vector. And then this week homework, one has to do the following thing. So lead derivative of x of the some differential form is defined limit t goes to 0 phi t star omega divided by t. So this is a so-called lead derivative of the differential form. Omega is the some differential form. And we can do the similar thing for the metric. So therefore, one can just consider Lxg is limit of t goes to 0 phi star t g minus g divided by t. If this is x is a Killing vector field, of course the numerator is 0, so that the lead derivative acts on g is equal to 0. And if you use local coordinates, this lead derivative can be written as the following way. So xk. So if you use a local coordinate, for instance, okay, you can take patch and you just consider local coordinate is x1 dot xn. So that the x can be written sum of xk and delta xk. Sorry. So then this equation, killing vector, this derivative acts on G is equal to 0, can be written locally is xk partial k g I j. So this is local expression by using local coordinate. So this is the condition for killing vector field. And this equation often appears in a GR. When you learn GR, killing the vector field show up. This is a killing equation in local coordinate. So one can derive from this definition to this one. This is the exercise for you. Anyway. First, you need to solve the exercise here. So once you solve this homework in problem, I don't know which problem I was, but this is a problem 2, I think, in this week homework. Once you solve this one, you understand what it means, this one. So, yeah, so it's good to solve homework. Okay. Let me move on. So given a metric G, there is a isomorphism between the vector field and one form. So given a Riemann metric, so there is isomorphism one can construct. The isomorphism between the vector field and one form. This is isomorphism. So it's an infinite dimensional vector space, but so this is induced. So I call G hat in the lecture note. So G hat acts on some x. So now it's inside the omega 1. So therefore one can just take the contraction between another vector field. X is a vector field. X and Y are vector field. So once you apply this isomorphism, so this isomorphism is defined by using this metric Gxy. So given a two vector field, one can have that product with respect to this metric G. And this product will give you one form with contraction with vector field. Okay? So their element of C infinity of n. It's a function now. Once you take the product between two vector field, it gives you the smooth function. So assignment, so as I mentioned, G, the tangent vector xp and yp, okay, this will give you some number. And once you smoothly move the point P over the manifold, you get a smooth function. And this g hat x is now one form, so one can contract with vector field, you get a smooth function. Okay? This smooth function is defined gxy. Contraction of x and y with respect to metric G. Any question? Do you know why you can have isomorphism? Does anyone know? Can you answer? Why you get the isomorphism? Which property do you use? Which property of the metric do you use to construct isomorphism? Speak out. What did you say? Which property of the metric do you use to construct isomorphism? Just speak out. Good. It's used the property of non-degenerate. So what we have done is essentially, so given the local coordinate, so the vector field has a basis. So these are bases for vector field. And the metric have Gij, Vxi, and Vxj. Once you act partial xi, let's see, xk, what you get G essentially ik dx I. Okay. So once you act, so G hat indeed G hat. So G is can be written as Gij dxi cross gxj dxj. Okay. And essentially, so this isomorphism, this map is just taking contraction between ddxk with this one of the differential one form, okay? And then you get the gik dxi. To get isomorphism, this gik has to be non-degenerate as a matrix. So that's what she said. So gik is non-degenerate means it can have inverse metric, okay? Inverse matrix at a point P or any point P. So to get the isomorphism, as a vector space, you have a map from one to the other that is performed with gik, but from the other, you need to have an inverse map to have isomorphism. So therefore, this Gij has to have an inverse map. That is a condition called non-degenerate. So determinant has to be non-zero. So to get the isomorphism, you need to have the non-degeneracy of the metric. Okay. So let's take a break. 10 minutes break.
to have some detail about the length of curve L gamma. Why it will be 3i3 then
So what we did is essentially, so there's a segment A to B, and maps to some curve. Yeah. And what I GI jamming is some point P. And from point P to the tangent vector. Right? And that what we are going to do is take open patch and map to flow from N, and at this point the curve looks like this curve looks like this one.
这个田数在这儿，但你的作业中途，
So this curve is mapped to the curve inside Rn. And here, so if you compose gamma and this phi, which is x1 to xn, then it's mapped from A to B to Rn, right? And this curve, this is the composition of gamma and phi. This is mapped from, this is parameters x1t. Okay? And this length is indeed Gij
About the pullback, does pullback always exist? I'm a little confused. Like, if you have a map from M to N, is like. So there's no inverse map. That does pullback exist in this situation?
So, given a smooth manifold M and N, smooth map, always manifold M, but 2 point can go to the same point, that's true. But at every time, the tangent is sort of like, let's go TP1, and this is TP. So let's go P1 and P2, and let's go Q. So there's a map. There is always linear map from one tangent space to this tangent space, and this tangent space to this tangent space. The F define the map, linear map TPI. This is linear map. As a vector space. So always have a map of the vector space to one copy of the tangent space at point P here to here. And this point P map to Q. It's a linear map under the as a vector space. Linear map means star this is what Leo. So therefore, you can always have G star of H star of the point X. You can always have vector xp1, so xp2, yp2 is the map G star xp1. Let's go pi. So you can always have, even if you have the 2 points mapped to 1 point, locally the tangent space is mapped to this tangent space as a linear. So the tangent vector always can map to this tangent vector here. And then the tangent vector here can always take a product with respect to Riemann metric G here, tangent space. Here also tangent space mapped to here. So the vector space, tangent vector can be always mapped to this tangent vector here. So here you can always have an inner product. So therefore, here, this inner product here, to define this inner product on this point, you just only look at the inner product here. That's why you can always have the pullback of the metric. Do you understand?
I'll think about it. Thanks.
Yeah.
He long ago
What?
We can construct this shape by identifying
on the plane, but if we apply Gauss-Bonnet theorem, the curvature of the 4G polygon is 0, but the all Euler characteristic is 2 minus 2G. You have give us the example is 1 torus. So the K is 0, but if G is not 1, it's not
So this is the question. I mean, so therefore, this means that the curvature has to be something else. So I'm going to explain that, for instance, genus 2 can decompose the following way. So you can cut. So if you have a genus 2 surface and then you can cut along this yellow line, then what you would get is as follows. So if you cut the Riemann surface, you get this. But here, in fact, this is no longer flat space. No longer flat space. For instance, given the Riemann surface and cut along the yellow line, topologically you get this. Topologically you get this. How to say enveloping. But you cannot project to the flat space. You cannot project to flat space, and then it's a really good question. And the metric should have. So in homework 4, I introduced so-called Poincare patch. Here, in homework 4, I will introduce Poincare patch. It's kind of one under actually. So Poincare disk. So it's a unit circle, unit disk. But the metric here is it's kind of an answer to the homework. So the metric is not standard metric. So as you approach to the unit circle, so denominator becomes close to 0. So therefore, this length here is the same as some of this length here. So that's what he means in this Poincare disk. In this word, not only so now we introduce metric here. If you introduce this metric, the length here is the same as this small, look like small length, but it's the same length. And if you compute the curvature for this, and I will introduce so-called geodesic from now, but I mean geodesic is given the 2 point, there is some so-called shorter distance one can consider. And now, if you look at for instance, these 2 points, it's a kind of answer to the homework. These 2 points, this is not the straight, the shortest distance indeed. Along this, in this metric, so the shortest distance becomes like this way. So it's called hollow cycle. So therefore, it's not standard metric. And then, so one can just have the following. So therefore, the reason why I just draw like in the no straight lines, instead of straight line, I just draw like a circle like this. So the reason why that this is geodesic, and then one can have like this way. To construct genus G-Riemann surface, and then inside here the curvature is no longer 0. And if you apply the Gauss Bonnet on this one, you get the correct Euler crystal. So that's sorry, can I get downstairs to get a drink? I just keep answering questions to the student. I didn't have time. So let me go to downstairs and get a drink and then let's meet.
反过来呢？
对，这句话对应这个情况。
这里你是看见这个。
它是正和虚的一个说。
你这里是这个 f，那如果是这里的话，你那不是你平行数算它长度就变了？
没有变，那如平行只要是看回来的这个电子才能才合不合原来的式。
道理就虚，它肯定正合的。
如果它打定回来的话，原来这个不平行，说明这个的有那种区别。这叫那个王。
但是王特斯确实有那个。
王特斯没有那个。
是这边的问题。
就是你没有那平区别的话，你可以用任何一张纸把它给，就像圆柱那样的对。但是这个它反而有那平区别。
So let's continue. Yeah, so since there's a lot of questions, it's a good sign. So you're trying to understand something. Okay, let's continue to study Riemannian geometry. Okay. So now we saw the isomorphism between vector space and then between vector field and the one form. And then just want to introduce the notion of so-called gradient vector field. So f is some smooth function over the manifold to R. This is a smooth function. And then one can introduce the notion. So we already saw that this, if you apply the exterior derivative, you get the one form. Okay. So now we have isomorphism between vector field and then one form. So the question is, what is the corresponding object? What is the corresponding object in the vector field? So that's what we are going to think, and which is called gradient vector field of F. So this is called gradient vector field. So sometimes it's written like a nabla of F, whichever you want. I mean here this construction is just using that one. G hat df Sorry. What I'm doing? Sorry. So df oh my goodness. I'm already somehow exhausted. Okay, so this is where X is a vector field. So this is how you define a gradient vector field. And locally, so essentially what we are doing, for instance, if you the height function to the F, So it depends on how you define. I'm not sure what. I think this is just a. Let me. Which direction it is? So it should be locally this graph f. Locally Gij df dxi and partial ddxj. So this is the local expression. Just use the Einstein convention, and I think what I did is that if you use f as a height function, for instance, height function, the gradient vector field is essentially anyway, so the gradient vector field is something like this shape. Here I assume, of course, M is a torus with metric, induced metric from R3. So Mg. So this is gradient vector field for f if you use the height function. So therefore there is 4 critical points. So one is the bottom and top, and there is a saddle point in the middle. So these orange are critical point. These point are critical point of height function f, and also it becomes critical point is first derivative with respect to local coordinate is 0. So therefore it becomes 0 of gradient flow, gradient vector field. Okay, so let's see. Okay, so let's see the notional gradient flow by using. So it's just dual of the df. It's a dual of df under this isomorphism. Okay. And the physicists always try to do calculation. I mean, if you work on general relativity, or like whatever, supergravity and so on, you have to be very, very fluent in local current. And often people use so-called orthonormal frame. So orthonormal frame or sometimes it's like so the local current you always have, so Gij is indeed symmetric, and then positive definite, and also non-degenerate. Therefore, this is some locally at point P, so you can always have by using linear transformation. So the linear algebra will tell us that always you can diagonalize the coordinates. There exists coordinate transformation such that Gij is equal to delta Ij. So which means that roughly speaking, so there is a point P, and so manifold Mg, okay, and the map from here to Rn. Schematically, usually people, dx direction, one can take whatever direction for x, but one can just usually map the x1, x2 coordinate like this way, x1, x2 coordinate like this way, but you can always take these local some nice coordinate transformation such that the if you do like this way, at this point, at least at this point, you can have x1, x2, a standard x1, x2 in Rn. So that's what it means. So therefore, in this coordinate, you just have usual EI, A, Ej, A. What I meant is that the Gij is EIA and Ej. The for instance, the simplest example. I'm already exhausted, as you can see. Simplex example is as follows. So for instance, if you use the polar coordinate for is this the correct polar coordinate metric for R2? No. What is the correct polar coordinate R2? Can you write that? This is okay. I just got confused about it. I think it's R3 becomes R3. Okay. Yes. Sorry. Oh my goodness. This is R3. Is it correct? No. Oh my goodness. No, you don't need it. Yeah. Okay. So this is R3, polar coordinate R3. Sorry. So therefore, locally the metric is something like 1 R squared sine squared theta. So one can just introduce a notation that the EIA is delta IA such that maybe E1 is just dr, E2 is just R d theta, E3 is just R sine theta, d phi. Okay. Then the metric is E1 square plus EI square sum I 1, 2, 3. That's the also normal frame in the polar coordinate. So with the polar coordinate. Yeah, of course. Now I just consider R3 and just origin is removed. Then it's well defined in the metric on the R3. Okay, so this is the also normal frame. And then usually this orthonormal plane, people want to, I mean, usually physicists want to work on this orthonormal plane. If you do the research in GR, always you need to do that. And then in 4 dimension, it's called, is it 4 dimension? In 4 dimension, it's called Vierbeins or tetra. Tetrads or Vierbein. It's a German language. So this E1 to E4 or is called Vierbein. Its Vier is 4 in German. And but for German dimension, it's called Vierbein and so on. I mean, it's just notation now. That I don't care about notation and so on. But anyway, it's just name. Vierbein. Vier is many in German. Vier means many in German. Can anybody speak German here? No. Okay, so the reason why we introduced the metric is the from here it's going to be very deep. One can introduce the so-called Hodge star. I didn't tell you anything about the reference. So I didn't tell you anything about the reference. I think in the first page 4 whatever. I just mentioned that the textbook and reference in the lecture note in section 1.2. For mathematics book, I mean, I listed many things, but for differential form, I personally like this Morita's book for differential form. This is really good for differential form. And for usual, so this the usual differential geometry, shallow geometry. This ST67. Who are the authors? I already forgot. ST. Yeah, single solve. And solve. This is very thin book, but it contains very essential part of differential geometry, and it also contains lots of. I mean, it's a mathematics book, so you can just read it, proof. In this section, I omit all the proof. Instead of giving proof, it's a lecture in front of physicists. So I just want to tell you what it means and also how to use them. And then, so from here, we are going to talk about a very deep subject. So this is not easy book, but it's very nice book. Warner's book. This is the what is the name? Lie group and the differential manifold, something like that.
Foundations of differential manifold.
Yeah, foundation of differential manifold Lie group. And from section 5 and 6 contains the proof of Hodge theorem. And I'm going to talk about the Hodge theory from now. But the Hodge theory is very deep theory, and then I just give some brief introduction to the Hodge theory. But the Warner's book just treat this so-called harmonic form by using analysis and so on. I mean, I mean, this like how to say differential geometry by using analysis, it's called analysis, geometric analysis, and then Xintao Yao, how to write that? Xintao, I already forgot. I should have. Huh? Like, Yao is really geometric analysis.
Everybody uses content.
Yeah. So Yao, he got a fused metal. Is the really the one of the really true experts on geometric analysis. And this harmonic form and so on. Yeah. So I'm just going to introduce Hodge theory. Introduce the Hodge theory, but it's very deep theory. And if you're interested in, you can look at the Warner's book section 5 and 6, as far as I remember. Okay, so that's the textbook. Yeah. So. And there are many books for physicists too. I just listed 4 of them. To be honest, I don't like none of them. For me, at this level, it's better to read mathematics book and translate physics language into the translate physics to the mathematical language by yourself. That's what you guys doing. What you guys doing in homework actually. That's one of the. That's why I try to give lots of homework to get used to how to translate physics language to the mathematical language, or just try to look at physics in terms of language and mathematics. Anyway, so I just listed it, but as I mentioned, the Miller's book, I listed 2 books. One is the differential geometry, topology from differential geometry, viewpoint from differential geometry. That one is, I think, thinnest book among them, but wonderful read. Miller's book is always wonderful. And then also I also listened to the Moore theory, and then I already erased. So gradient flow and so on will appear in the Miller's book, in the Moore theory. So these 2 Miller's book is the seriously wonderful read and the most read book in the mathematics. And you should know this guy's name. Yeah. So Mina also got a fifth now. Okay, so let's go into talk about the Hodge theory a little bit. So once you introduce Riemann metric, one can consider so-called Hodge star. So Hodge star is just a simple operation. So given that Riemann, this mg is now I just consider oriented, and then essentially closed. I think I prefer to consider closed, which means there is no boundary, compact and without no boundary, closed manifold for simplicity. And a Riemannian manifold, Riemannian. So M and G are Riemannian manifold. Then one can introduce so-called orthonormal frame by using Gram-Schmidt process on each point. So the Hodge star, one omega k is just mapped from, so this n-dimensional, n minus k of m, of course I assume m, in such a way that so if you introduce one can e1 dot ek, the basis is mapped to e plus 1, which so each basis e1 to ek is mapped to the complement of the differential form. This is called Hodge star. So we definitely need Riemann numeric G to define a Hodge star. That's a very important thing. So to introduce orthonormal, okay, orthonormality, one has to use a metric. Okay? Therefore, to define the Hodge star, so one has to introduce a metric. In particular, if you look at the constant, Hodge star of the constant is just a constant function. It's just omega 0. Its element is, so therefore it becomes top form once you apply the Hodge star. Then it becomes E1 En. That is called volume form. It's a volume form. And if you use, instead of this orthonormal coordinate, if you use just standard whatever local coordinate, the volume form is, as you're familiar, you might be familiar with from the GR. Square G dx1 dx1. Okay, so. And in particular, so how to pronounce in usual Mandarin? But why his name is Yao Xinta?
Because it's local.
Counting. And this geometric analysis is very, very important in physics. For instance, in GR, for instance, positive energy theorem and so on, or and rigidity and so on. Anyway, rely on these in this geometric analysis. In particular, I'm already super exhausted. For instance, omega can be written down J1 total Jk dxJ1, which dxJk. So local coordinate K form can be written like this way, and once you apply Hodge star, so one can just write down 1 over K factorial, and you just apply the some epsilon tensor, so which you give it just sign. So therefore I don't care so much about but it's important once you try to do the calculation. So this is times what I'm doing. I'm sorry. Yeah, I think I'm correct. So this is how we work. Local coordinate, I just already used the Einstein convention, just sum over all Ji and all that and so on. So this is the how you write down the hot star in terms of local current. And as you can easily see, definitely you need a metric to define the hot star. This epsilon 1 is just a standard epsilon tensor for sine. So important thing is the hot star needs metric definitely. Okay, and then one can do the following calculation. So now we can do the following operation. Where should I erase? Should I write here? So omega k, by using hot star, omega n minus k. But now we can apply the exterior derivative, then you get the n minus k plus 1. But now up to sine, you can consider the following object k minus 1. So here, star d is exterior derivative. And we already know that this star, if you apply k minus 1 in the star, you get this one. And we want to have some object in such a way that this path is equal to this path. Okay? So that's we call delta. So delta is defined by minus 1 and k plus n plus 1 star d star omega. So this is the object we want to consider. So then, if you use the standard property of the hot star and the exterior derivative, one can easily show that the delta square is essentially up to plus minus sine star d star d star, and star will give you just sign. So just give you some plus minus sign. So therefore it should be star d square star. And we know d square is equal to 0, you get 0. Okay? So delta is also delta square is also 0. And also one can show that the by construction star delta d is star d and this can be understood as sum up to sine d star star. Therefore d delta star. Okay. And one can do the same thing for the same exercise. D star delta is equal to d star d star. So therefore, up to sine d square star, which is 0. And the same thing for happen delta star b. You can do the same exercise. these are property of the delta square and also these properties. So now we can introduce some notion of the. So in the if you in so in Riemann manifold, one can introduce the metric G is essentially the vector field times vector field bilinear form to C infinity of M. And if you use the isomorphism, one can also have some inner product in the one form. C infinity of M. So this is essentially here you get the Gij, and here essentially you get in GR people just write down Gij upstairs. It's just inverse metric. But now, if you use this Hodge star, and we assume the M is oriented close to Riemann manifold, then one can introduce so-called inner product in the omega k. So this inner product, linear metric, will give you the inner product vector field on one form. But if you introduce Hodge star, one can just introduce the omega eta is k form. Then inner product of this one is just the omega wedge star eta over n. Or if you use just the usual convention, I mean this is also this one. So this is the inner product between K form. So in other words, so this is K form, this is K form, and this is which form? N minus K. So if you take wedge product of N minus K and K, you get the top form, omega n. So one can integrate over the cross manifold oriented. So that's how you define the inner product of the K form. So therefore, one has to do integral here. Okay. So that's why you need an analysis. And in particular, under this, so why this d and delta are the just cross cousin is that the in addition to delta square is equal to 0, and also under this inner product, one would have the following relation. It's easy to verify. Eta is equal to so d omega wedge star eta m, and this is same. Right. What should I? Oh, okay. Sorry. My brain's no longer working. So this is equal to minus omega wedge star. Right? So, and we know that it's closed, so this is 0. Therefore, okay, and then this is equal to, if you just be careful about sign, this is omega delta eta. Okay. So essentially, essentially what we are having d star eta, and now star, okay, and this becomes delta, Okay, this becomes delta, and this star star cancel with this minus sign. Okay, that's how you get it. So therefore, so here, if you have an inner product and one operation is dual to the other operation, so D delta is adjoint. It's called adjoint to D. So on a cross-oriented manifold, D and delta are the same object in fact. It's just dual. And in particular, one can define, so this delta, capital delta, delta D plus D delta, which map omega k to omega k. Okay. So this is called Laplace-Bernoulli operator. And also, if MF delta or in general, so omega equal to 0 for, so this is called, omega is called harmonic form. And in fact, so this Laplace harmonic form, and in fact, this as you can easily see from here, one can just have delta omega eta is equal to omega delta eta. So it's called self-adjoint. It's called self-adjoint. Oh. Okay. And then now, this is the how does it bold H K of M. So if you consider the harmonic form, and then the theoretical Hodge decomposition is the following. So omega k of M. So now I already assume M is oriented to closed manifold without boundary. Is equal to hk of M plus omega k minus 1 of M plus delta omega k. So I just state the statement of the Hodge decomposition. To prove this one, you need a hard analysis, and the Warner book did that. Does it for you. So if you're interested in the proof, you can just take a look at this proof. And moreover, but as you can easily see from here, so here this is called what? We learn, right? What is it called? D omega k minus 1 is what is it called? So exact forms. These are called exact form. And then delta omega is some analog exact form for delta. And as you can easily see, if delta omega equal to 0 means that if only if. So as you can easily see, for all harmonic form, this is true. So as you can easily see, this is self-adjoint. And then as you can easily see, so for instance, delta omega, let's see, delta omega eta is equal to d delta d omega eta. Therefore, it can be decomposed as delta omega delta eta plus d omega d eta. Okay? Okay? You understand? So if I just use this property, d omega is equal to d omega eta is equal to omega delta eta. Okay? So therefore, once you apply d something becomes delta eta. Okay? So therefore you get this one. The same thing, delta something is the same as d eta. So you get this one. And then once you apply eta, if delta is so one can indeed this is again non-degenerate. So therefore delta omega equal to 0 if only if delta omega is 0 and d omega is 0. Okay, do you understand? So therefore here if you have cross form with respect to d and delta, it's the same as harmonic form. Okay? But however, this Hodge decomposition mentioned harmonic form actually exclude exact form. Okay? So therefore, Hodge theorem mentioned that this is theorem by Hodge. It's a deep theorem. Is isomorphic to dynamical homology. Okay. This is isomorphism. Oriented compact Riemann manifold. So essentially dynamical homology is indeed harmonic form. So that's what Hodge tells us. Okay, so it's a deep theorem. You need a really advanced technique in analysis. When I was a student, I read this book, and I already forgot everything, so I cannot tell. Yeah, but it's a wonderful book. Anyway. Okay, so let me state Poincare duality and finish. So this Hodge theorem tells us that so for non-trivial, you can have always harmonic form as a representation of dynamical homology. In particular, once you take eta, so omega is dynamical homology or harmonic form, the same as harmonic form. Let's take harmonic form. It's dynamical homology of M. Then you can take the eta as the star of omega, and the inner product of the omega is indeed omega wedge star omega. Anyway, M and then wedge eta. And this is the always non-zero. This is always non-zero. and this is always non-zero, and also so therefore this leads to so-called Poincare duality. Such that one can always take, given the Riemann cohomology, of n to R such that omega eta so this is non-degenerate. So in other words, so eta is also here, eta is also h n minus k, because due to, since delta star is equal to star delta. Oh, sorry, I think the other one. So once you apply, so delta eta is equal to delta star omega, which is star delta omega, which is 0. So now assume omega is harmonic form. Seems like I need to filter a little bit. So since omega is harmonic form, this is 0. But once I operate the star and delta, the harmonic operator, Laplace Beltrami operator, commute. So therefore, eta is also harmonic form. Okay, you understand? So delta eta is equal to 0. Therefore it's harmonic form. But now it's eta is just star of omega, so it's therefore n minus k form. Okay. So therefore, you can always have, once you take star of omega, you always get non-zero element. So therefore, you get the, as a matrix, the pairing between case Riemann cohomology and case n minus k Riemann cohomology. Take wedge product, you get the non-degenerate pairing. So this is called non-degenerate. So in other words, the hk of drum is isomorphic to h n minus k from as a vector space. As a vector space. This is isomorphism. For compact orientable Riemann manifold. So this is the Poincare duality. So K's cohomology is an isomorphic to n minus k cohomology for compact orientable Riemann manifold. And you will see the example in the sphere and also torus case in the point. Okay, let's finish, and then so next lecture I'm going to talk about the Riemannian geometry, so which is very important in physics to describe the GR. Okay, let's finish.